In this video, we're going to continue looking at different modes of failure, but this time we're going to focus on failure due to working and environmental conditions. And we're going to look at each of our material classifications: metals, ceramics, polymers, and composites. So let's begin with metals. In an earlier unit, we looked at the degradation of different materials, and in particular we looked at the corrosion of metals. We spent some time talking about copper and how copper can degrade, first of all to form copper oxide and then to form copper carbonate. But one of the things that we noted when we spoke about the corrosion or the oxidation of copper was in fact it was a preferential process. It created a surface that was hard, but it also created a surface that was resistant to further corrosion. And we're going to speak about that property a bit more in a moment. We also looked at less favourable forms of corrosion, such as rusting, and we talked about how steel can degrade as a result of contact with water and oxygen. So we can see in the short video clip here that what the water and oxygen does is it attacks certain sites on the steel's surface and it causes degradation. We can see that this clearly isn't a preferential process because the material is breaking down, it's flaking, and this is having an effect of decreasing the strength and the preferential properties of the steel. So it's by no means a preferential process. Now, another type of corrosion to consider is something called stress corrosion cracking. And when we looked at non-destructive inspection techniques, we looked at how these types of defects can be found using magnetic particle inspection. But what we need to do is understand why these stress corrosion cracks occur. And the name indicates the reason: stress and corrosion. What we're looking at in the image here is the outside of a pipework, which would probably be carrying gas under pressure. Now, as a result of that pressure, there's going to be stresses on the outside surface of the pipe. Those stresses actually open up the surface of the material and enable corrosive agents to get within the cracks. So here we have a combination. We have stress and we have corrosion combining to form these stress corrosion cracks. So what we're also interested in really is how we can prevent these types of degradation. Now, the key to preventing things such as rusting is to prevent the water or the oxygen from attacking the surface of the steel. So one method would be to use painting. A disadvantage to this is any areas that the paint didn't cover would still leave the surface susceptible to rusting. And if there were any cracks in the paint, then moisture would actually seep into those cracks and cause further damage. Now, another method that's used extensively is something called galvanizing. And in galvanizing, steel components are actually dipped into a bath of zinc, as we see in the image here. So what the zinc will do is it will coat the steel. It will also fill in any defects and crevices within the steel. And because it's molten, we get much better coverage throughout the surface of the material. The interesting thing, however, is that zinc is more corrosive than steel. The zinc will actually oxidize, and after oxidizing, a carbonate layer will form due to reactions with carbon dioxide in the air. But this brings us back full circle to copper, because zinc carbonate, as with copper carbonate, is actually corrosion resistant. So in effect, the steel is coated with zinc, the zinc corrodes eventually to form zinc carbonate, and what we end up with is a non-corrosive surface to our steel component. So the zinc is actually sacrificed in order to form a non-corrosive surface. There are other types of degradation that can affect our metals, such as erosion, and we saw in the previous tutorial how erosion can cause pitting and scuffing on the surface of components. Now, once again, we're interested in how we can prevent that, but before we can understand how it can be prevented, we need to understand what the surface of a material actually looks like. Now, the surface of a material under a microscope, we would see that it has surface asperities. And on the diagram on the right, we can see a representation of what asperities are. It's basically due to the roughness of the surface. Even if we were to look at a smooth surface, such as glass under the microscope, it would still have these apparent asperities. The size of the asperities would be dependent on the roughness of the material, but nonetheless, all materials would have these asperities. Now, what the lubricant would do is it would actually sit within the crevices of the asperities, levelling off the surface. So here we see an example of how lubricants can in effect coat the surface and minimise the impact of those asperities. So ensuring that we have the correct lubricant and we have the correct quantity of lubricant is really important to reducing wear on things such as gear teeth. So the next classification of materials that we're going to consider are ceramics. And the type of failure that ceramics tend to be susceptible to is thermal shock. Now, thermal shock occurs when an object is heated or taken to a very high temperature, and then it's cooled rapidly. Now, that rapid cooling causes internal stresses, which causes the component to crack or fail. And we'll talk a bit more about how that can be prevented in a moment. So thermal shock occurs in a single cycle. An object's hot, such as the dish we see on the right hand side here. When it's cooled suddenly, the internal stresses cause the material to crack. Now, if we think of something more closely related to engineering, we've looked at how ceramics can be used for things such as car brake discs. Now, there's another type of thermal shock known as thermal fatigue, which is a combination of thermal shock and fatigue. Now, essentially what's happening is an object's being heated and then cooled, heated and then cooled, and over time that causes a fatigue effect within the material. And consequently, over time, we can get cracks appearing throughout the material. Now, to a certain extent, these effects can be overcome. So first of all, it's important to understand what causes the thermal shock. And what causes the thermal shock is a thermal gradient. And by a thermal gradient, we mean different areas within the material are at different temperatures. So if we use our example on the right-hand side here of the cooking dish, when it comes out of the oven, the material is hot, and the material is hot throughout. That heat has had time to conduct throughout all of the material. But if we were to take that dish and place it in cold water, then the surface cools rapidly, whilst the inside of the material is still hot. So the outside is cooling and trying to contract, whereas the inside is hot and is remaining expanded, and this causes the stresses that eventually lead the material to crack and fail. So one way to prevent thermal shock is to cool the component gradually rather than suddenly. And another way would be to either change the material or modify the material such that its thermal conductivity increased. That would mean when the surface is cold and the internal regions are hot, the transfer of heat through the component would happen more quickly. Now, another way of preventing thermal shock is to use materials with lower thermal expansion. So when we have the temperature gradient existing throughout the material, the expansion and contraction rates are going to differ. Now, an example of where this is used is in Pyrex cooking dishes, and they use a variant on glass called borosilicate glass, and it has a much lower thermal expansion than regular glass. And the final method that can be used is tempering. Now, tempering is a heat treatment process, and in effect, it locks internal stresses within the component. So it actually locks compressive stresses within the component, and then when the component expands and contracts, it's working against those compressive stresses. So in actual fact, it's relieving the stresses that are built into the structure of the material. So next we have our polymers. And once again, we've talked about polymer degradation in an earlier unit. Now, in particular, we're going to look at UV degradation, but various other different degradation processes, such as thermal degradation, follow a very similar process. Now, on the right-hand side, we have an image of the polymer polyethylene. And if polyethylene is going to degrade by UV degradation, then it's going to go through 3 stages. The first of those 3 stages is initiation. Now, in initiation, the UV radiation, or the thermal energy, is going to break a hydrogen bond. Now, in breaking the hydrogen bond, the carbon is going to keep its electron here, and the hydrogen is going to keep its electron here. Now, what that means is we're going to have 2 highly reactive free radicals. Now, there's various different reactions that can occur, but one would be the reaction with oxygen. So our highly reactive carbon there might react with oxygen in the air, and what we can actually end up with is a group that looks something like this: oxygen, oxygen, free radical. So once again, we've created another highly reactive free radical. So now we have the hydrogen, which wants to go on and react. We have an oxygen here, which wants to go on and react. And we have various other different reactive agents. The important thing to point out here is that during this stage of propagation, there's all number of different reactions that can occur, and it was all as a result of the initiation from the UV light. Now the final stage is termination, and in termination, these highly reactive free radicals actually combine together to end the reactions. But the point is, until termination occurs, these reactions are damaging our polymer. They may be causing it to become weaker or more brittle. Now the way that this can all be overcome is by preventing the UV light from breaking that initial bond, so preventing initiation from occurring. And the way that's done is using something called stabilizers. And in particular, to prevent UV degradation, a stabilizer known as benzophenone is used. And benzophenone is an additive that's added to the polymer when it's molded, and in effect it absorbs the UV radiation, and it prevents the UV radiation from attacking those bonds. There's various other different stabilizers to prevent thermal degradation and chlorine-induced cracking and various other different degradation processes, but for the purpose of understanding how it can be prevented, benzophenone is used to absorb the UV radiation. Now finally, we're going to look at composites, and for composites we're going to return to the mode of failure of fatigue. And on the right hand side we have an SN graph for carbon fibre reinforced polymer. Now there's a couple of important things to point out on that graph. First of all, the scale on the x-axis goes up to 1 × 10⁹, or 1 billion cycles. So we're talking an extensive number of cycles. But what you'll probably notice is that we don't have a fatigue limit. So in metals, if the stress is suitably low, then we can assume that the material has an infinite life, but we don't see that with composites. It means that any degree of stress can eventually cause fatigue. Now perhaps more importantly, what you'll notice is the unpredictability of these results, and I'll give you some specific examples. At a stress level between 40 and 50% of the failure stress for this particular sample during testing, what we notice is a very broad spread of data. And what we're going to look at is the black triangles, which represent tension or failure due to tension. So at 45%, moving right, we see during one test, the material failed in 1 × 10⁵ cycles, or 100,000 cycles. But we see in other tests that that material failed at closer to 1 billion cycles, 1 × 10⁹. Now that's a huge difference between 100,000 and a billion. So the material is very unpredictable. And we could repeat that for different stresses. So again, at stresses around 75% of failure stress, up here, we have tests where the component has failed in 1 × 10⁵ cycles, or 1,000 cycles, and we've had other tests where it's failed closer to 100,000 cycles. So there's a huge amount of variance in those results, which we wouldn't necessarily see in metals. Metals are much more predictable. Now the reason for this unpredictability is that there's more than one way that carbon fibre reinforced composites can fail. And we see some different examples there. We can get cracks within the matrix itself. We can get individual fibres fracturing. We can get debonding, which is essentially where the polymer resin detaches from the fibres, or vice versa. And we can also get fibre pullout, which is a result of debonding, where the fibres actually separate themselves from the composite matrix. So what this means is that for certain applications, composites are not suitable, particularly in areas such as aerospace. So although they're very strong and very light, their unpredictability means that they can't be used in industries such as aerospace, where safety is of paramount importance and safety factors that are used are generally relatively small. So to summarise, in this video, we've looked at failure due to working and environmental conditions. For metals, we've considered corrosion and erosion. For ceramics, we've considered thermal shock. For polymers, we've considered UV degradation. And for composites, we've looked at fatigue in relation to the unpredictable behaviour of carbon fibre reinforced polymer.